Thank you everyone for attending today's Foxconn Quantum Computing Seminar. Today we have the pleasure of having Andrew Projansky, who will tell us about Gaussianity and simulability of Cliffords and Matchgates. So Andrew is a PhD student in the group of James Whitfield at Dartmouth College. His interest is in the understanding of quantum and classical border, studying fermionic systems and the ways in which these systems can be mapped onto spin systems. And this talk will be about some recent work on the complexity of Clifford and Matchgate hybrid circuits. So Andrew, the floor is yours.
Great. Yeah, thank you so much for having me. Yeah, my name is Andrew, as introduced. I know that in Taipei right now, it is the 13th. Where I'm at, it is still it's still the 12th. And yeah, today I'm going to be talking about some recent work that that we've done in our group that I've had the pleasure of doing with a good friend and collaborator, Jason, as well as my advisor, James Whitfield, about Gaussianity and simulability of Cliffords and Matchgate circuits. This is based off a paper that was recently published in JPhys A. You can find it on arXiv as well as JPhys A. All right, so let's begin with kind of the motivation for, why I'm studying what I'm studying, what the words in the title of this talk really mean. So we can think about problems in quantum information theory, and many problems, at least, if we're dealing with, pure states, look something like the following. We let some state psi be, be resulting from some unitary gate acting on some initial state. And we often really want one of two things if we're doing some problem related to quantum information. We either are looking for bit strings and marginal outputs. For example, given some circuit, what is the probability that you might measure some subset of qubits to be all zero? And we also might look for expectation values. This is important, if we're dealing with studying the energy of some Hamiltonian that we're interested in. That's an expectation value. So a typical problem statement in quantum information can kind of be rewritten as a statement of given some state, compute or sample from the probability distribution that describes that state, or compute some expectation value of some observable that you are interested in over that state. Now, it's important to ask, though, when does this problem actually require quantum resources? And the answer is very much so not always. At some level, we know that we have very nice classical approximations to many systems of interest in quantum, but we can also study this question from a slightly more rigorous complexity theoretic lens. So in this talk, I might mention some things about complexity classes. If you're not familiar with complexity theory, that's all good. I'm only going to really ever mention three classes. I'm going to mention the class P being the class of problem solvable on, a deterministic classical computer in polynomial time. This is things like, is a number prime? Or, we kind of think about it more generally as easier questions that we can handle possibly analytically on our laptops, just on our sheets of paper. These are problems that we know how to solve efficiently. I also going to talk, this is about quantum information theory, so I'm going to talk about BQP. BQP is kind of the equivalent of P, but for quantum computers. BQP is the class of bounded error decision problem solving that are solvable by measuring a single output qubit from some quantum circuits. For example, Shor's algorithm is an algorithm that we know to be in BQP, and right now we don't suspect it to be in the class P. We expect that we need a quantum resource to actually solve Shor's algorithm. And then the final class that I'm going to talk about is something called post-BQP, which is BQP with the ability to post-select on measurement outcomes. It's important to note that post-selection and post-BQP is somewhat unphysical. We shouldn't expect to have the ability to do post-selection if we're dealing with some problem that we put in a quantum computer. But post-selection becomes something important when we study simulability, when we start to study these problems that might look quantum but actually don't end up being quantum. The ability to have post-selection or not, and the ability to essentially reach some sort of counter arguments to say, hey, if we could simulate this with post-selection, then XYZ outcome would happen in terms of complexity theory that we don't conjecture to be true. So post-selection, while unphysical, is going to be an important tool that we're going to use. But I do want to emphasize that post-selection is an incredible amount of power to ask for your system. But very often, if we have some simulable systems, we often actually do get post-selection. Now, if we have just any quantum state, let's say we have all of Hilbert space, and we say, okay, I'm interested in some arbitrary, completely random quantum state. And let's assume that I can efficiently prepare it on a quantum computer. In that case, then, it being some completely random, arbitrary quantum state, we know that problems like getting expectation values or sampling are problems that are going to belong to BQP, that we really are going to assume that we need quantum resources for those problems. But not every problem, that's not true for every single problem. For example, we can kind of define or think about these various families of what I'll call classically simulable quantum states. States for which, if you want to get expectation values or compute samples or probability distributions of, we don't actually need to use the resources of BQP. We can actually just do so with the resources on our laptops or on our notebooks without having to deal with this added complexity that quantum might give us. And so the motivating question for a lot of the work that we're about to discuss is to better understand when quantum resources are needed or not, by better understanding essentially this landscape of what I'll call classically simulable states. These quantum states that maybe might look quantum at first, but really we can handle with resources completely classically. And at this point, it's good to start getting into a bit more of the details, reviewing simulable circuits. And along the way, we'll really review a lot of interesting aspects about how we describe both fermionic systems on fermionic systems by themselves, and how we describe fermionic systems on quantum computers. So as a reminder for everybody, or in case you're unfamiliar with kind of some of the notation around describing systems of fermions. Fermions are essentially indistinguishable anti-commuting particles. We know that for example, we know that we cannot fill like a fermionic mode with two particles at the same time. That comes from the fact that they are indistinguishable and the fact that they are anti-commuting. That is enough to essentially give us back the Pauli exclusion principle. So that's kind of a physical perspective. Mathematically, what we see is that if we're describing some system of fermions, we require that the operators that we're describing those fermions with have a specific anti-commutation structure. We also have the ability, though, to slightly change the anti-commutation structure. For example, you might be familiar with creation and annihilation operators. These you might call Dirac fermions. These have a certain anti-commutation structure. Often, though, for some of the work that I do, it's actually more useful to work with slightly rotated operators, some linear transform of your creation annihilation operators into what are called the Majorana operators. There are two really ways in which Dirac fermions and Majorana fermions are different. Majorana operators differ because Majorana operators are Hermitian when creation annihilation operators are not necessarily Hermitian, as well as if you look at the anti-commutation structure for the Dirac fermions carefully, they do differ from the anti-commutation for the Majorana fermions. The Majoranas all mutually anti-commute. And that specific anti-commutation structure that we can use to describe fermionic systems will end up being very useful later, especially when we want to transition from studying fermionic systems to studying systems that systems of, Pauli's, systems of spin Hamiltonians that we might consider on quantum computers. So if I have some fermionic operators, the goal is almost always to express some fermionic Hamiltonian. These are Hamiltonians which describe usually interacting fermionic systems. For example, the molecular Hamiltonian is an interacting fermionic system that has terms that are quadratic in the creation annihilation operators, as well as quartic in the creation annihilation operators. It's important, though, to note that if we didn't have this quartic term, let's say in the molecular Hamiltonian that we're seeing here, that will leave us with a Hamiltonian that just has quadratic terms. And if you just have a Hamiltonian that's quadratic in your fermionic operators, that's often called free fermion, or you might see the literature say Gaussian. These in literature are effectively, they mean the same thing. It means that because there's no interaction term, we can efficiently diagonalize these Hamiltonians by, a very nice Bogoliubov transform. And thus, we can very exactly study the entire spectra of these free fermion Hamiltonians. Free fermion Hamiltonians are also interesting, not just from the perspective of we can solve for the spectra very easily, but free fermion Hamiltonians also give easy time evolution. For example, if we were to take the exponentiation of a quadratic fermionic Hamiltonian and then conjugate a single fermionic operator, we only ever actually rotate between 2n fermionic operators. Essentially, we conjugate a single fermionic operator. What we get back is a possible sum only of single fermionic operators. Conceptually, this can be understood by the fact that the algebra generated by free fermions is exponentially smaller than the Lie algebra generated for, say, some arbitrary unitary gates. For arbitrary gates, we know that, we're dealing with a Lie algebra, which is, exponentially scaling. There are 4 to the n Paulis. If we're dealing with free fermions, however, the Lie algebra for that system is polynomially tractable. And thus we have some very nice properties when it comes to the time evolution generated by these free fermion Hamiltonians. So this, in some sense, ends the discussion of free fermions, though actually we will see that we will come back to it from a slightly different perspective very shortly. Before we do so, though, we have to briefly review Cliffords and stabilizer states. I'm sure that many of you, almost all of you, if not all of you, are familiar with the Cliffords. The Cliffords are an incredibly important set of gates to quantum information theory, often heavily utilized within the theory of error correction, for example. But the interest that I have in them is more so due to the fact that Clifford circuits are this other class of simulable circuits. Clifford circuits are circuits generated by essentially 3 gates. And then we can also define some set of stabilizer states to be the states that come from acting on, some computational basis state by some Clifford. And these circuits are simulable. These circuits have been known to be simulable for an incredibly long time. The celebrated Gottesman-Knill theorem tells us that for any stabilizer state, if we want to get probability distribution outputs or we want to get expectation values, we can do so classically. We don't need to harness the power of quantum to study Clifford circuits. We can do so incredibly efficiently. The Gottesman-Knill theorem tells us that, and then there's been a number of previous works, previous works from today that go into all the details in which we can efficiently represent these circuits. It's important to note, though, that Clifford circuits, in some sense, are very, very close to being universal. Beforehand, we had the Clifford circuits were generated by 3 gates, the C-naught, the Hadamard, and the phase gate. if we were to add another single gate to that set, specifically in this case, the T gate, though there are many possible candidates for a gate that you could add that will essentially elevate the Cliffords. But just this single T gate is enough to take us from something that is completely simulable, that we can do in our laptops very easily in P, to the ability to make universal quantum circuits and essentially require that we need the resources of BQP. And often, especially when it comes to error correction, the way that you actually might introduce a T gate, this kind of universally enabling gate, into your system is something called a magic state gadget. A magic state gadget is something which utilizes quantum teleportation in order to teleport essentially the action of the T gate onto some part of your circuit by essentially having the T gate act earlier on some ancillary system and then doing some adaptive measurement to essentially teleport the action of that T gate onto the actual bulk physical circuit that you want to implement that T gate onto. And while this is often used in constructions for fault tolerance, we'll find that our interest in the ability to do kind of these gadget magic teleportations has some implications for some proofs that we will see in terms of computational complexity. And now with the Cliffords discussed, we actually will start to come full circle back to fermions, which is that, remember, Cliffords specifically act on Pauli strings. The Clifford, you can think about a Clifford as being the operation which takes a single Pauli string to another single Pauli string. Now, there's a relationship, though, between fermionic operators and Pauli strings. This is seen the best through what's called a fermion to qubit transform. A fermion to qubit transform is a transform which allows us to map some set of fermionic operators to some set of spin operators, some set of Paulis. We do this, and we're able to do this with Paulis that share the exact same anti-commutation structure as our fermions do. You know, we know, for example, that our fermions have some specific anti-commutation structure. We define, for example, the most common fermion to qubit transform being the Jordan-Wigner transformation. And if you were to study the resulting Pauli strings carefully, you would see that they have the exact same anti-commutation structure as the fermionic operators. And not only can we do this for the creation annihilation operators, we can also do this for the Majorana operators as well. And often we'll find that in terms of thinking about the correspondence between fermions and spins, that's actually a little bit easier to deal and think with the Majorana operators. So mostly going forward, if I'm discussing fermionic operators, in our heads, we should be thinking about Majorana fermions, and then dual, as we'll see, you know, these single Pauli terms. It's important to note, though, you know, Jordan-Wigner is a single example of how we might construct a set of anti-commuting Paulis that shares the same structures as fermionic operators do. We could ask for any set of Paulis that has the same exact anti-commutation structure as our fermionic operators do, specifically now dealing with the Majorana operators. So we require these Paulis to all mutually anti-commute. Well, we recall that conjugation preserves anti-commutation structure. If I have some set of Paulis, all of them mutually anti-commute, I now conjugate every single element of that set by, let's say, a Clifford. What results is a new set of spin operators, Pauli operators, that are guaranteed to mutually anti-commute. And thus, they are 100% a valid way of representing our fermionic system with a different set of Paulis, no longer Jordan-Wigner, but, you know, we have access to every single set of mutually anti-commuting Paulis in terms of all the ways in which we can represent our fermionic system on our quantum computers. And there are some implications to the ability to do this. For example, you might study specific Hamiltonians of interest. For example, the XX plus YY chain in one dimension. It's very well known, it's been known for a very long time, that this Hamiltonian XX plus YY is exactly solvable. We can exactly solve for the spectra of this Hamiltonian, specifically by using the Jordan-Wigner encoding. We use the Jordan-Wigner encoding. What we get back is a quadratic fermionic Hamiltonian, and as we know before, that means it is free fermion, and free fermion means it's solvable. But we also might have some other Hamiltonian of interest. For example, let's say we had the XX plus YY chain conjugated by some Clifford. And maybe we don't even know it's conjugated by some Clifford, but maybe we have some spin Hamiltonian. Well, it might be that if we were to try to use Jordan-Wigner to study that spin Hamiltonian, maybe we'd get back some dual fermionic Hamiltonian that looks incredibly complex and we have a lot of trouble thinking about and kind of dealing with. But it's possible that there was some other choice, some better choice of mutually anti-commuting Paulis, such that this spin Hamiltonian that maybe looks, or that maybe looks very complex, is actually, again, free fermion solvable. And thus, we actually kind of approach a bit of duality, kind of two ways of actually seeing this picture and what we're trying to do here. Specifically, we're about to talk about conjugated matchgates, conjugated dynamics. Essentially, we'll have some Clifford, some free fermion circuit, and then some Clifford. But we're going to see that these conjugated circuits, these circuits that arise from studying these different ways of combining simulable things together, actually has a really nice physical intuition as well. They correspond to the time dynamics generated by free fermion solvable Hamiltonians. Not necessarily free fermion solvable only with the Jordan-Wigner encoding, but free fermion solvable with some encoding such that all of my Majoranas that I choose are single Pauli operators. So at this point, I might have thrown around the word matchgate a couple times. And this is because often in the literature, when someone says the word matchgate, they might actually be referring to just time dynamics generated by free fermion Hamiltonians. But it's important to note that there is a distinction between just time dynamics of a free fermion Hamiltonian and matchgates. Specifically, it's that matchgates, these circuits that have been known to be simulable for some time, specifically come from mapping the time dynamics of a free fermion Hamiltonian to the time dynamics of a free fermion, of a spin Hamiltonian that is solvable under the Jordan-Wigner mapping. So matchgates specifically have a very well-studied structure. Matchgates look like these parity-preserving 2-qubit local gates, and there's a very important restriction that essentially you have an even parity sector and an odd parity sector. And the individual matrices that kind of make up each of these sectors, it is only a matchgate if these matrices have the same determinant. As a concrete example, the fermionic swap gate, or F-swap as many people call it, is a matchgate. This -1 that you see is essential for ensuring that the determinant of the even parity sector is the same as the determinant of the matrix defined over the odd parity sector. However, you might say, okay, well, F-swap is a matchgate. What about swap? Swap is not a matchgate. Swap does not match this determinant condition. And you actually can prove that in the same way that the T gate is the gate which elevates the Cliffords from being simulable to being universal, it is the same thing for the swap gate and the match gate. Match gates beforehand make up some set that we can study very efficiently on our laptops, on our pens and papers. If we add swaps to our gate set, we can now generate universal quantum circuits again, and thus, we need the power of BQP to study match gates where we also have the swap gate that we can do. But if we don't have a swap gate, then match gates can be simulated efficiently. We've known this for some time. The reason why, though, they can be simulated efficiently is very different than the Cliffords. The Cliffords, we might think about taking Paulis to Paulis and having, for example, this nice stabilizer tableau representation that we can track efficiently. Match gates, their simulability is better understood due to the efficient ability to calculate the Pfaffians of antisymmetric matrices. So most problems when you're dealing with some match gate circuit, you're going to get down to some value that will look like computing a Pfaffian of an antisymmetric matrix. But for antisymmetric matrices, the Pfaffian is just the square root of the determinant. And we know that we can calculate determinants efficiently. And thus we can calculate these outputs efficiently. We can do this both if we care about getting marginals or bitstring outputs. If we care about asking, okay, what's the probability of measuring the first 5 qubits to be all zeros for some state. But we can also do efficient expectation value calculations. In this case, we use a slightly different structure than maybe we saw in the last slide. We use a covariance matrix, and it turns out that by taking the Pfaffians of submatrices of this covariance matrix, we get back the expectation values, for example, over Pauli operators. And now at this point, we've reviewed some simulable circuits, we've reviewed fermion to qubit transforms, we've touched on match gates, and we kind of have touched on how there's kind of a certain duality between fermions and spins. We have some fermionic system, we can represent them with a number of possible different spin systems. And now we can look into specifically what happens to questions about simulability when we try to study the time dynamics under these different fermionic Hamiltonians, or equivalently, when we try to study the time dynamics or try to study these problems that we might do in quantum information when we have some Clifford and Matchgate hybrid circuits. So these elements kind of acting together, specifically when we have Cliffords conjugating our Matchgate, or we have a Clifford following our Matchgate circuit. So, as we just said, match gates are simulable. It's important to note, though, that match gates are simulable. We can do all these bitstring outputs, even if our input state is a product state. There are a number of ways actually to realize this. One way is to recognize that there's essentially a gadgetized device that uses a single copy of the plus state as a sort of catalyst state, and then from there allows you to build up a product state only with match gate circuits. But we had this cost of an additional single ancillary state in the plus state. We also, though, could have done a slightly more mathematically motivated mapping where we consider some now unphysical spin Hamiltonian, or unphysical fermionic Hamiltonian, I should say, that has both quadratic and linear terms in our fermionic operators. But there actually is a mapping where by adding a single additional fermionic operator, we can actually map this back to a purely quadratic free fermion Hamiltonian. And thus, again, we get kind of these more generalized match gates, but all of the very nice properties that we had about time dynamics, we still keep when we do this mapping. Either way, product states are essentially within the allowable inputs for simulating match gate circuits. Product state, it's fine. We can do that. We can study the evolution of product state under match gates and still get expectation values, still get efficient sampling, still get probability distribution calculations. But what about for conjugated match gates, or equivalently, as we say, other free fermion solvable dynamics? Maybe said otherwise, and maybe an interesting question specifically on the topic of product states, And actually, one moment, I have to open a door very briefly. There was a cat gnawing at the door that was making a bit too much noise. All right, back. And now you might ask, a slightly separate question. What are the fermionic encodings that have the generators required to make arbitrary product states? As we have argued, we know that for the Jordan-Wigner encoding, specifically if we're dealing with matchgate circuits that we know are free fermion under Jordan-Wigner, that product states are allowable inputs and we can make them via just these free fermion dynamics. If we were to choose some other fermion to qubit encoding, some other way of picking some anti-commuting Pauli operators to describe a fermionic system, do we still have the ability to make product states? And the answer is no, besides swap conjugated encodings. So the only encodings such that product states are Gaussian, such that product states can still be made under the dynamics of free fermion Hamiltonians, are just with the Jordan-Wigner encoding. And if we were to conjugate the Jordan-Wigner encoding by arbitrary swaps. Essentially, the proof of this breaks down into essentially 4 parts, all of them having to do with the allowable ways that you need, of the allowable operators that you need to generate arbitrary product states, as well as the possible constructions of mutually anti-commuting sets of Pauli operators. And what you find is that if you want a mutually anti-commuting set of Pauli operators that can still construct product states, the only ways to do that are if you choose the Pauli operators given to you by the Jordan-Wigner encoding with the freedom of allowing some swaps on that encoding. As a corollary, for swap conjugated matchgate circuits, we know that things like bitstring outputs as well as expectation value outputs are simulable on product state inputs. So essentially, these circuits are exactly equivalent to if we didn't conjugate by anti-swap, just by doing some pretty trivial classical processing either on both sides, on our input and our output. But it's important to note that it is only these circuits such that product states are still these allowable inputs. Specifically, okay, you might say, okay, let's start to go beyond just swap conjugated Jordan-Wigner encodings. Let's consider maybe swap and control Z conjugated Jordan-Wigner encodings, and thus swap and CZ conjugated matchgate circuits. For these circuits, bitstring outputs are simulable specifically on computational basis state inputs. If we have a computational basis state and then we want to measure some bitstring outputs, then again, kind of in the same way that we saw before, where with some classical processing, we can move around lines and inputs and outputs in a certain way and still retain a simulable circuit. We can do the same thing here. We can move some things around cleverly and end up again with a simulable circuit equivalent to a matchgate circuit. But, oh, and before I actually say more, specifically, it is important to note that the fermionic encodings that correspond to swap and control Z conjugated Jordan-Wigner encoding is specifically the fermionic encodings such that fermionic occupation is stored locally. For the Jordan-Wigner encoding, if you encode some set of fermions with Jordan-Wigner and then you say, okay, I want to probe this system and study the occupation of some fermionic mode, you only need to get the expectation value of a local operator. If you have swap and control Z conjugated matchgate circuits, this is still true, that to study fermionic occupancy of some mode that you've encoded into your qubit system, all you need is a local operator. This is no longer true when you go beyond just swap and control Z conjugated matchgate circuits. This essentially is a border where if we try to add any other Clifford to the set, we start to have fermionic occupancy be represented by some expectation value over some non-local Pauli operator, possibly. Now, with that kind of physics motivated note aside, we've discussed so far that these circuits are simulable on bitstring inputs, but they are not simulable on product state inputs. And this is both true from what we saw before for the proof that it is only the Jordan-Wigner and swap conjugated Jordan-Wigner that gives us back product states. But we actually have a slightly stronger statement, which is that not only are product states not kind of allowable inputs, not inputs that we can make from swap and CZ conjugated matchgate circuits, but actually the ability, if we could simulate these swap and control Z conjugated matchgate circuits on product states, we actually would show that we could classically simulate post-BQP, this class that before we said was this incredibly powerful, incredibly unreasonable, even physically unreasonable computational complexity class. The way that you would see that you could simulate post-BQP is by the fact that if you had swap and control Z conjugated matchgate circuits on product state inputs, you could use a circuit like the one presented here to specifically prepare the magic state for matchgate circuits. So in the same way where beforehand we had some, when we talk about Cliffords and T gates, where we had some magic T state that kind of enabled Cliffords to be universal, well, if we could simulate this, then we could classically simulate circuits that had all of these magic input states in them. And if we classically simulate them with post-selection, well, that would mean that we could classically simulate all of quantum computing. Said otherwise, product states for these control Z and swap conjugated circuits become resourceful. Simulability on a more technical, and if we want to even talk on a more technical level, for any complexity theorists in the room, simulability would imply a collapse of the polynomial hierarchy to its third level. And if you're not familiar with what the polynomial hierarchy is and kind of the arguments of complexity theory, I think the overall takeaway is to note that if we could simulate these circuits, then there really is no division. There would really be no division between classical and quantum resources. And we're going to make an assumption that there is a division between them. We're going to assume that, quantum computing is actually useful for some things, and that there really are problems that on our laptops, on our classical computers, we cannot solve, that we need quantum resources for. And now, I know that we're getting a little bit close to a time to wrap up, maybe take a few questions. The only other thing that I think I'll say for now is consideration about, Clifford-matchgate hybrid circuits, these, different ways of pairing these separate simulable resources together into single circuits. And now instead of conjugation, we'll specifically look at having some circuit that starts with a matchgate and then has some Clifford following it. Particularly, we'll ask the question about, can we still calculate expectation values efficiently? And the answer, actually pretty trivially, is yes, we can still calculate any expectation value we want classically. The way to see this is that the final Clifford layer, when we consider an expectation value, conjugates whatever Pauli we might consider into some other Pauli, because we know that the Cliffords take a single Pauli to a single Pauli. And now we end up back in a problem where we have some matchgate circuit and we want to compute the expectation value of some Pauli, which we know that we can do efficiently. We also, as a dual picture, instead of kind of wrapping up the action of the Clifford into the expectation value we want, we actually do have the ability to instead consider the covariance matrix that we kind of were using to take these expectation values and rewrite our covariance matrix with respect to these new conjugated Majorana and Pauli operators. But either way, we retain the ability pretty easily. We can see we retain the ability to get expectation values efficiently. Okay, so why do we actually care if it's efficient? Why, if it's kind of easy to see? Well, it's important, I think, from a perspective of what does it mean to be simulable? Or, what fundamentally maybe unifies both Cliffords and Matchgate circuits, both stabilizer states and Gaussian fermionic states? There's a nice perspective from Bravi from a paper from about 20 years ago that specifically defines what it means to be Gaussian, not in terms of, taking the exponential specifically of some, quadratic, but rather instead from the perspective of fermionic operators. And the definition that Bravi gives is that a state psi is Gaussian if and only if the specific condition based on your fermionic operators holds, that this tensor product summation over all of your possible fermionic operators has to be 0. We can now ask, okay, well, what are all of the states for which this is true, for which I can even ask for some set of fermionic operators such that the summation is true for some state? And it's interesting, it is an interesting perspective that if we start to think about going beyond Jordan-Wigner and going to these, other fermionic qubit encodings, either by conjugating by some Clifford or conjugating by some arbitrary unitary circuit. In that case, then, we can show that for any state, if we allow for our Majorana operators, if we allow for the description of these fermionic operators to be as complicated as we might want them to be, in that case, then, any state, we can make this summation 0. And thus, if we allow for completely arbitrarily complex Majorana operators, okay, well, now we say that all states are Gaussian. So obviously, we need to make some restriction to how we might use this definition from Bravi. And the restriction that we're going to place is we're going to require our Majoranas to be single Paulis. From the perspective of just asking for Majoranas to be single Paulis, there is no distinction between Jordan-Wigner and any of these other Clifford conjugated Jordan-Wigner encodings that we have looked at. And if we use this perspective, we actually can see kind of two things, two interesting facts emerge. The first is that all of these states that look like a matchgate acting on a product state, followed by a Clifford, are all of these sets in Hilbert space, such that they are Gaussian with respect to some choice of mutually anti-commuting Paulis. And maybe something slightly even more fundamental is that for all stabilizer states, so for all states that we have, some Clifford acting on some computational basis state, there exists a choice of 2n mutually anti-commuting Paulis such that our stabilizer states fit this Gaussian definition from Bravi. And thus, when we start to allow our fermionic operators to be represented by these different sets of mutually anti-commuting Paulis, we see that all stabilizers, by this definition, are Gaussian. And thus, we kind of get some unification of what it means to be simulable. The Cliffords and the Matchgates, in terms of how they act as circuits and how we understand the simulability, they often are very disjoint. Cliffords really come from mapping Paulis to Paulis. Matchgates come from the time dynamics of free Fermi Hamiltonians. They're not the techniques you use to show that one is simulable or the other is simulable aren't really the same. But nonetheless, when we study the composition of these things, we actually see that there is more Similarity then might meet the eye at first. We see that both Matchgates and Cliffords, as well as many of these hybrid circuits you might consider of Matchgates and Clifford resources together, represent states such that there is some choice of mutually anti-commuting Pauli such that they are Gaussian by this definition from Bravi. And thus, maybe when we consider studying the layout of Hilbert space and all of the simulable or not simulable states in that Hilbert space, we have access to more simulable states than just Matchgates and Cliffords alone. We actually can consider all Gaussian states instead, and kind of consider the combination of both Matchgate and Clifford resources together. And with that, I think we have about 10 minutes left. I'm happy to take a couple questions. I want to thank you all so much for both inviting me as well as listening to this talk. And yeah, please feel free to ask any questions as well as email me if you have any questions that come up later. And yeah, I'm just very grateful for the opportunity to talk to y'all.
All right, thank you very much. It was a very splendid and interesting talk. Yeah, so yeah, we have some time for questions. If you have a question, please feel free to just unmute yourself and ask now.
Yeah, hi Andrew. I just wanted to ask in relation to this perspective where you look at Cliffords as or stabilizers as a special case of Gaussians. Does this give you a means by which to extend stabilizers to some continuous group like we get with Majoranas normally, or with Matchgates normally?
I think that is a very, very interesting question that I actually do need to admittedly study more. But I can say that there are some interesting connections between stabilizer states, between Cliffords essentially, and essentially these very special convolutions of free bosonic states. So there's been actually some recent work that I'm forgetting who the authors of are, but they actually make this argument or kind of make this correspondence between free bosonic states and stabilizers. And so I would imagine that you could essentially go backward, start from stabilizer states and say, okay, what does the continuous limit look like? And what you would get is that you'd get back to Gaussian bosonic systems instead.
Sorry, what limit are we taking here?
So the limit is specifically, I believe, a sequence. So if you have some Gaussian bosonic state, I believe the limit that people take here is specifically a sequence of essentially convolutions that take our continuous bosonic problem to some finite problem, and the endpoint of that sequence of convolutions that people have been kind of thinking about in the literature ends up being the stabilizer states.
So like I think of convolutions as like an integral, like in probability theory. What convolutions are we doing in state space?
Right. So this is where I don't have the answer off the top of my head, but the language that people use is specifically the language of convolution. Specifically, if you look at some recent papers that kind of talk about simulability in general, as well as specifically like Gaussian bosonic systems and Gaussian fermionic systems, they often will specifically use the word convolution to talk about this process of taking free bosonic states towards stabilizer states. But yeah, that's a detail that I don't have off the top of my head.
Okay, if you have like a reference for that, I'd be very interested.
Yeah, if you send me your email, I'd be happy to send a paper to you. Right, I just don't have them off the top of my head, but I know that like they're, I think, a couple tabs away or a couple, go back into my history, and I think I had some of them up recently. So
yeah, alternatively, you can sort of send it to me, and I can send to everyone in the group too. Yeah.
Great. Yeah, I'd be happy to do that. Like I said, I don't have it in memory, but specifically, I've seen folks use the word convolution specifically, kind of study this process of thinking about this sort of limit of these Gaussian bosonic systems and how they essentially map back to stabilizer states.
Awesome. Thanks.
Right. Okay, so maybe give some chance to other people. Okay, maybe I can ask a couple of questions myself. So when you were talking about this, I think like the conjugated one, like swap and control Z. So it's only simulable if you said computational basis, I think. Is
Right.
that the only basis of product states for which it will be simulable? Or is there a different choice?
So if we want to get into some details, I mean, technically there exists some product states that aren't quite computational basis states, but maybe are a single non-Gaussian resource away from being computational basis states. And thus there might be some perturbative methods where, okay, it's not exactly a match gate, but maybe it's the sum of two match gate circuits instead. But in general, the statement is the distinction between computational basis states and completely arbitrary product states. And there is a division where if you want the power for completely arbitrary product states, picks any random product state with 100% certainty, you're going to have that state would enable you, if you were to have simulability, that state would enable you to essentially do post BQP classically. So while there are these maybe small cases where, hey, maybe there's a state that's very close to a computational basis state, but it's still a product state, and maybe it's fine. In general, if you're picking from, the full arbitrary set of product states, you're going to essentially get a state that is resourceful, that allows you, that would allow you to do universal quantum computation with post-selection.
I guess like my question is a bit more naive than that. So it's sort of like, is there anything special about the computational basis? Is it because you conjugated with Control Z? If you conjugated with something else, then it would be a different basis, I would assume.
Okay. Yes. Okay. I now see your question. Yes, it is specifically because under the action of swap and Control Z circuits, the worst that happens to a computational basis state is that it goes to minus some other computational basis state. And thus you remain within the set of all computational basis states. It is right, but if we were to consider some possibly, product state that had, some amount of Hadamard or some amount of gates that produce superposition among individual qubits, then the action of a Control Z gate would now take us out of the space of product states, but to the space of possibly highly entangled states, where now it's incredibly easy to see that, wow, we really have a lot of quantum power within these states. So yeah, at I guess a more baseline level, we can really think about, okay, what's the action of this specific subset of Cliffords on these input states, and is specifically computational basis states that have such that swaps and Control Z gates have a very nice action, and you preserve the fact that you're a computational basis state input.